And I'll hand over to you to talk about electrochemical CO2 capture.
Okay, thank you so much for the introduction and also for the invitation to speak at the symposium. I looked at the schedule, it looked very exciting, and I'm very sorry I'm not there in person. I've had too many colleagues test positive and they get not stuck, but have to quarantine and stay abroad for longer than they expected. And I have young kids, so I didn't want to travel abroad, but I guess they're releasing those restrictions soon. Anyway, I am in Irvine, which is in Southern California. We have a large electrochemistry initiative on our campus. This building that you see in the middle here was just constructed in the last year. It's an interdisciplinary science building with engineering and chemists, where we can, the fourth and fifth floor basically focus on a lot of electrochemical science and catalysis and separations. So I'll talk a little bit about the work that's going on in my group today. Oh, there you go. Okay, so I just wanted to briefly go over the motivation for some of the electrocatalyst targets that we're going after in our lab. A lot of it has to do with storing energy and chemical bonds, right? Because electrochemistry can basically help us drive redox reactions. And the motivation for this, which you're probably familiar with, is basically as a way to store renewable energy. So I used to live in the Pacific Northwest, and this graph, which is a little bit dated now, essentially shows in the month of April. In yellow is basically the solar energy generation each day, which of course only happens during the day, but if you've ever been to the Pacific Northwest, it'd be quite cloudy at times as well. So then there's less energy generation. Wind, of course, is very dependent on the weather. It can happen all day or night or not at all. So it's quite variable. And then demand, of course, is relatively constant. So this temporal mismatch between renewable energy generation and demand is a real problem. And there are many solutions for it for energy storage. And so one of the ones that has been proposed is, of course, we can use that energy directly when it's generated, but we can also use an electrocatalyst to store that energy in the form of chemical bonds. So as I said, there are many proposed solutions for energy storage, and this is one of them. It's probably better suited for potentially transportation or seasonal storage, since it's stable over long periods of time compared to, for example, a battery, and also higher density by weight and volume. So we can use an electrocatalyst to turn that energy, electricity into chemical bonds. And of course, we can use an electrocatalyst to then use that chemical fuel back in a fuel cell. This part is sometimes a little bit neglected compared to the energy, the fuel generation side, but thermal use of chemical energy, which of course is what we do now, is cardinal limited in terms of what we can get out. And of course, if we want to do this cycle, we want as high a round trip efficiency as we can get. An electrocatalyst in a fuel cell can in principle operate closer to 100% efficiency. Okay, so I often, in general catalyst audience, like to just briefly go over what an electrocatalyst is. I did not do electrocatalysis until I was a postdoc, so this was new to me. But we are very familiar, if you're a synthetic chemist or any kind of catalytic chemist, about redox catalysts. So here in the resting state is C. You can use a chemical oxidant or reductant to basically activate it into its oxidized or reduced form, C prime, which can then take substrate over to product, right? So this is a redox reaction at some catalytic rate. So when we do electrocatalysis, it's basically exactly the same chemically as what we do when we use stoichiometric redox catalysis, except we've replaced that reagent, the oxidant or reductant, whether it's zinc or permanganate or something else, with an electrode. And the electrode basically becomes the source of electrons or the sink of electrons, depending on whether you're doing reduction or oxidation. Okay, so a couple of parameters that are really important in electrocatalysts that, in terms of how we evaluate them, is one that's very commonly mentioned is the overpotential. So all reactions that we do, S to P, will have some thermodynamic potential associated with them. It's the free energy for that conversion. And then, these you could often look up as a delta G, but we can convert those to E naught. And then we have to apply some potential to the electrode to get C to go to C prime, right? Which is typically the reduction potential or oxidation potential. And the difference between the potential we have to apply versus what the thermodynamic minimum is the overpotential. So a large overpotential basically means that we're not very efficient. We're applying a lot of extra energy in order to get this conversion to take place. a nice thing about cyclic voltammetry or electrocatalysis analysis is that we can basically, at an electrode, if this catalyst is fast, basically it can turn over C prime back to C and go back to the electrode to pick up another electron for a reduction reaction. And then basically we can get an idea of what the rate is depending on the current of our electrocatalytic wave. And then another parameter that's very commonly mentioned is Faraday efficiency. I always feel like this is a little bit misnamed because, you know, when we think about efficiency in electrocatalysis, we often think about energetic efficiency. That, as I said, is reflected in the overpotential. But a Faraday efficiency is basically the yield of a product versus how many electrons are put in or taken out of the system. So it's basically using the electron as a limiting reagent or hole as a limiting reagent, and then seeing how much product is out. And of course, we want a high Faraday efficiency. It means that most of our electrons in a reduction are going to the product that we want. Okay, so there's been a lot of activity in this area of taking renewable electricity into chemical fuels. This mirrors photosynthesis, of course, which takes water to oxygen, and then the protons and electrons from that half reaction go to serve the other half reaction, which is the reductive side. There are a couple of products that we can get from these type of electrolysis schemes. One of them is the direct product of the protons and electrons that are generated from water oxidation. And that, of course, is hydrogen. It sort of is being very popular again in the US, at least as a fuel. It sort of had a dip in popularity over the last 10 years, but people are very excited about hydrogen again for direct water electrolysis. Of course, in the meantime, when hydrogen was less popular, we were very interested in liquid fuels because that is, of course, what we use now, and it's very convenient as a drop-in replacement for current fossil sources. And that could be something like formate, which is a liquid fuel, not a very energy dense one, or other hydrocarbons. And really one of the biggest problems when we do reductive electrocatalysis is selectivity. So, you know, there are times when we want hydrogen and we just have water electrolysis, but really what's a lot more complicated is if we want to go down to a carbon-based liquid fuel, is basically suppressing that hydrogen evolution reaction and getting mostly carbon-based products or high Faraday efficiency for those carbon-based products, if that is a target for our chemistry. So when we started working on this, we actually did start working on hydrogen first. And so one of the overriding principles in a lot of the heterogeneous catalysis is the Sabatier principle, which basically means that the optimal activity for a catalyst balances the substrate and product interactions. And these often end up being manifest in activity descriptor. So basically, it's a major bond making or breaking step that governs a catalytic rate. And for hydrogen evolution, it was often cited that the MH bond strength at a catalytic surface was that activity descriptor. So essentially, if it was too strong, that would sort of be where the catalyst would be limited in the breakage of that bond. If it was too weak, then it wouldn't form, and that would limit overall activity, right? So it's very Goldilocks, not too strong, not too weak for this bond strength. And if you look at these curves that are generated with the activity of hydrogen evolution catalyst, then they often exhibit in the form of a volcano, right? Where you have this optimal energy for MH bond strength for hydrogen evolution. And when we looked at this back when I started my career at Irvine, which is about 10 years ago, I'm looking at this metal H bond and I'm thinking, well, it looks a lot like a metal hydride. I'm a trained inorganic organometallic chemist. And to me, this can be reflected in the hydricity of this metal hydride bond, right? So it's basically like a hydrolytic bond cleavage energy, for example, of the MH bond. And so the question that we had was whether or not we could use a metal hydride bond strength as basically a descriptor for making hydrogen evolution catalyst, molecular hydrogen evolution catalyst. And in this sense that we could potentially tune it much more readily than in a lot of heterogeneous systems using the ligand environment, right? Which is of course what we do as molecular chemists, and get to optimal values with non-precious metals. So when we started doing this work, you know, if you look at this bond strength, let me move to my pointer. If you look at the potential bond strengths that are accessible, then it's about 0.8 EV, which I think is about 40 kcals per mole. And if you look at the metal hydrides bond strengths that have been measured at the time that we started, they basically span about that window. And so one thing that's notable about this data, obviously there are more points taken in acetonitrile than in water, is that these actually mostly represent metal bis-diphosphine compounds. So it's actually a very small set of ligands in our ligand repertoire or ligand toolbox. And we can still get a very high degree of tunability for this metal hydride bond strength. So you can see here in orange, all of these points, which span almost 20 kcals, is basically all different variants of a nickel bis-diphosphine. And the only thing that's changing are the R groups on the phosphorus and the backbone on between the two phosphoruses, right? What the bite angle of this ligand is. Additionally, just changing the metal can have a pretty dramatic difference on hydricity as well. So there are 2 points or 2 sets of compounds where you have a cobalt and nickel with exactly the same ligand set. So in this case, these are cobalt DMPE, nickel DMPE, and you can see that it shifts the hydricity by about 15 kcals per mole. And you can look at the DPPE derivatives as well. And this shifts also about 15-20 kcals per mole. So basically, there's a lot of tunability, either through ligand or metal identity for modifying this hydricity values. And again, in water, when we started this, there were not very many values, and we wanted to make catalysts initially that worked in water. So we basically decided to think about that a little bit more and try to make water-soluble catalysts and measure their hydricity values. Okay. So here's a proposed catalytic cycle for hydrogen evolution. You start with the metal, you reduce it by typically 2 electrons, protonate to make a metal hydride, and then that metal hydride is protonated to make H2. So this step of the reaction, we can actually basically write an equation for the free energy of protonation to make hydrogen from a metal hydride. And so this free energy of this reaction is basically dependent on the hydricity of that compound, the pH of the solution, which is the other reagent, and then the formation of the H2 bond, which is a constant. So, you can think about this reaction as you're basically breaking 2 bonds. You're breaking the metal hydride bond, which is why that energy is dependent. You're breaking an HB bond, which of course is reflected in the pH. And you're basically forming 1 bond, which is the H2, which is the constant. So what we did, we basically took this equation that reflects the free energy for hydrogen evolution for a metal hydride, and we drew it into a diagram like this. And so the way that this works is that hydricity, as you go down, becomes more hydritic, so it's a better donor or a weaker bond. And then on the x-axis is pH. And so in the green zone basically tells you what combination of metal hydricities and pH are stable, are prone to H2 evolution. So that means that delta G in this equation is negative, it's exergonic. So metal hydrides of these strengths and at these pHs will be prone to hydrogen evolution. And this should hopefully make intuitive sense, because as we get to a better donor, for example, sodium borhydride, aluminum hydride, you have a very low hydricity value, and those will be prone to H2 evolution, in water, any pH, for example, even at alkaline solutions. Whereas a weaker hydride donor may be stable at higher pH, which is reflected in this blue zones here. So in this blue zone, the delta G for this reaction is positive, so it's endergonic. So the first system that we looked at that was soluble in water was this nickel bis-diphosphine compound with these hydroxyls. So it's soluble in water and acetonitrile and several other solvents. And we measured that hydricity value to be 30 kcals per mole. So all of our hydricity values are not calculated. They're all experimentally measured using equilibrium measurements. And so this basically tells us that looking at our graph with a delta GH minus of 30 kcals per mole, that it should evolve hydrogen below pH about 3. So we tested that. We actually looked at it at pH 1. The reason why we went to such a low pH is that it's very common in electrolyzers because naphthalene is commonly used as the membrane. And so it's stable at pH 1 actually for weeks at 0.1 molar H2SO4. And shown here is the cyclical voltammetry. This is in gray is basically the background current. And then when we add our catalyst in, we can see an enhancement current, which is consistent with electrocatalysis. And again, we can analyze the current increase to get a rate of catalysis, which is about 1850 per second. When we do longer electrolysis at pH 1, we can get hydrogen production with greater than 98% ferritic efficiency. So the yield of hydrogen versus electrons we put in the system. And then furthermore, because it has these beautiful phosphine ligands, which allows us to use phosphorus NMR and it's diamagnetic, we can basically quantitate how much of our catalyst we put in before electrolysis and after electrolysis, and we see that it's basically completely retained. We don't lose any catalyst. So it's very stable as well at pH 1 for this system. Furthermore, we were able to do some mechanistic studies on this catalyst and show that we really understood that it was going through very likely our proposed catalytic cycle. This is the proton and phosphorus NMR of our resting state. So only one signal on the phosphorus NMR. If we add 2 equivalents of a chemical reductant, we can get down to the nickel 0 compound, which we then see in the phosphorus NMR very cleanly. We can protonate once to make the nickel hydride using triethyl ammonium. You can see in the hydride region of the proton NMR, we see that peak appear. And then if we add a stronger acid, then we can basically see the hydride disappear as it reacts, and then we can see H2 evolve in the proton NMR, and then we can see regeneration of our resting state, which is exactly the same as our authentic sample. So we could basically use stoichiometric electron and proton reagents to walk through this catalytic cycle and show that it's likely going through that nickel 2 to nickel 0 protonation once to make a hydride, protonation again to make H2. So, you know, like I said, sort of hydrogen was sort of fashionable for a while, and then it became less fashionable. People were more interested in CO2 reduction to make carbon-based fuels. And so the question was, you know, can we use what we learned about hydrogen evolution to get a better CO2 reduction catalyst? And so one of the biggest challenges in CO2 reduction is you have protons and electrons floating around. And it's very easy to make hydrogen. Typically, there's a low kinetic barrier for that. So we want to be able to suppress that reaction so we can get selectivity toward carbon-based products. And so one of the things that we often say in a group is a good CO2 catalyst that's very selective for carbon-based products is probably a bad hydrogen evolution catalyst, right? Because we want to suppress that reaction so that we don't get concomitant formation of this other product that's typically a gas and difficult to separate. So if we go back and look at our graph, what this basically tells us is also how to make a bad hydrogen evolution catalyst, right? So we know in this blue zone, that protonation to make H2 is endergonic. And so basically what this says is that at pH 7, our nickel hydride is probably very stable and will not evolve hydrogen. And we basically tested that doing electrolysis. So pre-electrolysis, we get nickel 2, and then we can reduce it by 2 electrons at pH 7, and we basically very selectively form the nickel hydride. So we don't see any H2 evolution. It basically does a 2 electron reduction protonation that stops. This is great if we want to be able to use that nickel hydride to then do a selective other reduction, since we know it's stable to protonation. So then the next question is, what kind of metal hydride do we need to actually react with CO2, right? So we want to basically divert this metal hydride that we're generating to react with CO2 instead. So it turns out that hydricity also governs the reactivity of a metal hydride with CO2 to formate as well. There's no proton dependence on this reaction. Basically, if a metal hydride is more hydritic than formate, then delta G for this reaction will be favorable. It will be exergonic. And so we actually know what the hydricity of formate is in a couple different solvents. So basically we need to know below that hydricity in order to make this reaction favorable. So in acetonitrile, the hydricity of formate is 24. And so what that tells us is that if our metal hydride has a hydricity below 24, it will be favorable to react with CO2 to make formate. And if it's above that, it will never happen. It's basically endergonic. And so with this, when we put this on our graph, what this tells us is in this region, both H2 evolution and CO2 reduction are both exergonic. That doesn't mean you can't get selectivity, but it would have to be kinetic selectivity. But we basically saw this region outlined here that shows that we can get selective reduction at these pH values and with these hydricities because H2 evolution will not be favorable, but CO2 reduction will be. So we basically modified our system. As you can see, our first nickel hydride is not hydritic enough to react with CO2, but we basically made it more electron rich. We tuned the ligand as we wanted to be able to do with these systems. And and we measured the hydricity, and it was about 23 kcal per mole. So it definitely can sit in this region. And we were able to show that it was stable to hydrogen evolution at pH 9, as we expect. But the hydride transfer to CO2 was really slow. And so one of the things about working in water at these alkaline pH values is that most of the CO2s there's not a very high concentration of CO2. Most of it's bicarbonate or carbonate. And we wanted to show that this region does in fact exist, and we can use it to design catalysts. So we moved back to acetonitrile, where we wouldn't have this bicarbonate-carbonate equilibrium to work with. We basically redrew this diagram. The only thing that we need to do to redraw this diagram is to know what these constants are in these solvents, which was already reported, the H2 hydrolytic energy and the formate hydricity. And then we looked at a known hydride system, this platinum system that has a hydricity of 41. And so we picked this one because it sort of had the right hydricity value for us to test this diagram to see whether we could get selective reduction. And so it says here that, if we're above a pKa about 30, then we can get selectivity for formate reduction. So a student, Bianca, worked on this project where she basically was able to synthesize both the platinum 2 compound, the 0 and the hydride. We measured the pKa of the hydride to be 31, and then this is sort of the pKa that you need to actually evolve hydrogen, which is 25. She showed that this, under the wrong conditions, can in fact serve as a hydrogen evolution catalyst. If you use triethylammonium as the acid, you evolve H2. But we showed that we can basically turn this off. So in the cyclic voltammetry, in black is just a 2-electron couple for the platinum 2 to platinum 0. This is under N2 in the absence of any substrate. And Bianca showed that if you add 1 equivalent of phenol, then basically you can selectively generate that hydride. So you get 2-electron reduction protonation. And the reason why there's no return wave is because now it's the metal hydride, the platinum hydride compound. And so then the question is, if we can basically do this 2-electron reduction, protonate wants to make the hydride, can we intercept that hydride to do selective CO2 reduction? And the answer is yes. And so in red was when we add CO2. And we can get electrocatalytic CO2 to formate reduction with very high Faraday efficiencies and a low overpotential. And so we show basically by understanding the thermodynamics of every step of this reaction, we can basically get selectivity toward the products that we want. So one thing that's unusual about this is, we selected this platinum compound because it sort of had the right hydricity that we were looking for. But of course, platinum is very well known for being a hydrogen evolution catalyst. And so by basically thinking about the thermodynamics and designing the right ligand environment around platinum, we were able to turn hydrogen evolution off for the system and get a very selective catalyst for CO2 reduction. Okay, so, at this point, I'm thinking like maybe 2 years ago, we were thinking if we could reduce CO2 to a liquid fuel with low potential, we're done, right? Because now we can take our excess renewable electricity and make our carbon-based, carbon-neutral fuels. So the elephant in the room that hadn't really been discussed much at the time was, where does the CO2 come from? If we want to move to this renewable carbon economy, we have to actually get CO2. And right now, it's not very, well, obviously when we work in the lab, we get it, we buy a tank of pure CO2. But the way that it is concentrated now from sources that are not cryogenic, it's not very efficient. And so you can calculate the thermodynamic minimum that's required to concentrate CO2 from various sources. From flue gas, we estimate is 10%. To 100%, this is basically just using this freshman chemistry equation to sort of figure out what your minimum is. The state of the art for flue gas capture are as alkylamines. These absorb CO2 under ambient conditions, and then if you heat them, they release the CO2 in a concentrated stream. Climeworks uses sorbent materials, which are desorbed through a combination of reduced pressure and heat. And the estimated energy cost of these is given here. So you can see that compared to the theoretical minimum, they're not very efficient. And so my student, Jeff Barlow, who has graduated since then, was sort of thinking about, we work very hard to lower the overpotential for our catalyst. And so if we think about this free energy to capture CO2 from an industrial stream to 100% with current technology and using a very good electrocatalyst to basically take that CO2 to CO, the capture part actually takes the majority of the energy in order to go from this flue gas down to your renewable CO. And it's very similar for air capture as well, that basically, the vast majority of the energy that you're using is actually in the capture step. So we really felt like there was space for us to work on CO2 capture and concentration in order to improve some of these numbers in this overall cycle. So as I've said, or I haven't, so the previous technology that's most common in CO2 capture and concentration is thermal cycles, right? Something absorbed at under ambient conditions, something absorbs CO2 from dilute streams under ambient conditions, and then is heated to be released. And so these are basically inherently Carnot limited in efficiency. The way that I think about this as a chemist is, of course, when we want this reaction to have a free energy that's negative, your delta S will be negative, so it will be working against you as you try to capture CO2. So in order to capture CO2 from dilute stream, you need a really, really large negative enthalpy, right? And so if you're going from a flue gas to like direct air, you basically need an even larger negative enthalpy. This is, a little bit simplified, but this is sort of generally true if you want that free energy for capture to be negative. The problem is that when you release, your enthalpy then swaps around in a thermal cycle. So now you have entropy working for you for release, but you're working against this enthalpy, this large enthalpy that you needed to capture from a dilute stream. And so you basically need to go to higher and higher temperatures in order to basically make release favorable, right? So this is very common in thermal cycles in general. And then often in the thermal cycles that are currently used for capture, achieving those high temperatures is not very practical because the sorbents are not very stable, those high temperatures. And so the idea was that, what we really need is something that can basically change the enthalpy of the sorbent so that we don't have to fight against it when we're trying to do release with some kind of a external switch. And so in our case, we're thinking about using an oxidation state as our switch, and then basically doing what we call an electrochemical CO2 capture and concentration scheme. So basically it'll go either, for or against capture or release, depending on the oxidation state. Okay, so there are higher theoretical efficiencies that are possible with electrochemical cycles over thermal cycles. Electrochemical cycles are not Carnot limited. And of course, you can, if renewable electricity is cheaper, there's an advantage there in terms of cost. And then we, of course, are allowed low temperature operations, which basically expands the amount of sorbents that we can use. You can get high pressure desorption, which reduces compression costs as well, which is a major cost right now. And it's extremely modular. It doesn't need a lot of infrastructure in principle to operate, unlike a lot of the current schemes for capture and concentration. So the chemistry side of this is that we actually need a redox carrier to basically have that enthalpic switch depending on the oxidation state. And so the idea is that you have a molecule that exists in two oxidation states, R and R minus in this case. And R minus has that, very strong favorable enthalpy for CO2 capture. Basically, it has a very high equilibrium constant. It can capture from very dilute streams. And then once upon oxidation, it basically loses that enthalpy for CO2 capture and releases it as well. So basically, the criteria that we have for a redox carrier is that it binds CO2 tightly when reduced, large K1 here, and it has a minimal affinity when it's oxidized, or a small K2. And the way that this could work in a very simplified scheme, I'm not an engineer, is that, we could have R minus in an absorption column, or it could absorb the CO2 from dilute streams, and then it can get oxidized in the concentration step to make a CO2 enriched stream. R can go back and get re-reduced to R minus, go back and absorb more CO2. So it's kind of like a CO2 pump, basically. If you think about electrochemical proton pumps, it's like a CO2 pump in this sense. Okay, so molecules actually that have these properties have been known for a couple of decades. Here's an example of one. Quinones have been very commonly studied for this purpose. So quinone, this tert-butyl derivative is shown here. In its fully oxidized form has basically no affinity for CO2. And its fully reduced form, it has a very high affinity for CO2. So the log K1 is 15, so 10 to the 15 binding constant. And so this is easily enough to capture CO2 from air. And in fact, that was shown that it was able to concentrate CO2 from very low concentrations to 100% in a single pass in an electrochemical cell. The problem is that this was under N2, or dilute CO2 in N2. It is not stable to air. And in fact, most redox carriers that have been used for CO2 capture in these schemes are all sensitive to air. And the reason for that is because oxygen is very easily reduced to superoxide. And if your reduced species for capture is too reducing or has a potential that is negative of this O2 superoxide potential, then you'll be prone to doing electron transfer to make superoxide instead of capturing CO2. So there's, a couple bad things about that. One is that your quinone gets oxidized again, so it can no longer capture CO2. And then the other bad thing is, of course, if you make superoxide, that can basically be very destructive for your capture agents as well. And so the third criteria that we have for a capture agent is that the redox potential has to be positive of the O2 minus couple in order to function in oxygen. So when we looked at all of the quinones that had been reported when we started doing this work, we looked at their KCO2s that had been measured and their redox potentials. So here we put this as log KCO2. And we see that basically they follow a linear free energy relationship, right? So compounds that are more reducing have a higher affinity for CO2. And then compounds that have a lower affinity for CO2 are more oxidizing. So if we look at the requirements that we need to capture CO2 from flue gas, we need about 10 to the 4 binding constant. So basically anything that is above here. If we look at atmospheric capture, we need things that are above 10 to the 6th, 10 to the 7th binding constant. And then, of course, our other criteria is O2 stability. So we need a potential that is positive of this O2 minus line. And so if we put those all together, we can see that, quinones or any capture agent should be in about this zone to do flue gas capture and in about this zone to do atmospheric. And you can also see that at the time that we started this work, there were no quinones that fell into this category, or actually any capture agents that fell into this category. And so we wanted to basically change that. My student Jeff was looking at this quinone, which is a tetrachloroquinone, because as you can see, it looks pretty close, right, to getting to flue gas. But clearly, if we try to modify this using our traditional electron donating withdrawing groups and Hammett parameters, we'll probably fall on this line again. So we basically need to find another way to modify the properties of this compound that doesn't involve inductive effects. And so what Jeff found was that in an old paper about quinones, lots of studies have been done on quinones over the decades, that if you add alcohols into their solution, then you basically get shifts in reduction potential for quinone derivatives. And so he basically tested this out on this tetrachloroquinone. And you can see here that at the first potential, you don't see any effect from adding alcohol. So basically this semiquinone is not affected by the presence of alcohols. But if we add alcohols, we can see large shifts in that second reduction potential to generate the dianion or the dianion species. And so basically what we believe is happening is that the alcohols are hydrogen bonding to the dianion, which stabilizes it. And then we get these large potential shifts up to 340 millivolts. Furthermore, we believe we can see these interactions using electronic absorption spectroscopy. So in black is the dianion under dinitrogen with no alcohol added. In dashed is the hydroquinone, so this is the fully protonated species. And then in the colored spectra, we can see the dianion with various alcohols added. And we see that shift that we believe is this hydrogen bonding interaction. But importantly, we do not see it match the hydroquinone. So basically, you're not doing an acid-base reaction. This is a hydrogen bonding interaction that we believe that we see with the dianion. So then the other question is, can we see CO2 binding when we have alcohols present? So here you see the 2-electron reduction to the dianion. And what we propose is a CO2 binding of this. We have some evidence by NMR spectroscopy that this is one CO2 bound to generate this species with this binding constant in the absence of alcohols. In the cyclophotometry in black, we see, the dashed black line is just the quinone reduction under N2 with no alcohols. When we add CO2, we get the dark black line, and that lack of reversibility and that shift is indicative of CO2 binding. And then when we add alcohols, we basically see a further shift, which we believe, again, is interaction of these alcohols with the dianion with and without CO2 bound to it. Again, Jeff looked at this by electronic absorption spectroscopy. You can see in solid black is the dianion in the absence of any alcohols, and then in dash black again is the hydroquinone. And then we can see when we add alcohols and CO2 to this, we see smaller shifts in that potential, which we believe indicates that hydrogen bond interaction. You see there's not very much with this terp-butyl alcohol, a little bit more with these other alcohols. And so essentially what we believed was happening was that we can basically get alcohols interacting with both the dianion and the CO2 bound dianion. And so normally what would happen when the absence of alcohols is you get 2 electron reduction to the dianion, CO2 binding. The stability of this is reflected in that KCO2. When we add a hydrogen bond donor, we basically see a large shift in the E1/2, the reduction potential, which is due to the stabilizing interaction. So the strength of that hydrogen bond directly affects the reduction potential. But the hydrogen bonding interaction could potentially also impact the KCO2 as well, depending on how it interacts with that, that CO2 bound species. And so it was quite a bit of work on Jeff's part, but basically he measured the KCO2 of all of these reduced quinones in the presence of alcohols and compared them to the redox potential shift. So what this graph reflects is basically how much of a benefit that you get for having a hydrogen bond interaction in terms of redox potential shift and binding. And the summary of this graph is that if the hydrogen bonding interaction is too weak, you don't get enough of a redox potential shift to really help you break that scaling relationship or disrupt that one that I showed in the beginning. But if the interaction is too strong, then you actually inhibit CO2 binding. And so there's basically a sweet spot in terms of alcohol pKa. You don't want it to be too strong or too weak. And basically here at 16, not only does having the alcohols added to solution positively benefit your reduction potential by shifting it past the O2 minus couple, but it actually enhances CO2 binding as well, that you actually get an increase in binding constant. So if we were to look at our new metrics, if we add ethanol to this TCQ solution in DMF, we can see that we are now sitting in a zone where we can get flue gas capture. So you can see the largest effect is in redox potential, and you get a small modest effect in improvement in CO2 binding. And so adding this alcohol basically improves both properties that are important for redox capture agents. We tested this. This is our setup. We are actually collaborating with engineers to do a better setup now that will allow us to cycle more and faster. But this is sort of a standard electrolysis cell. And essentially, what I'm showing you here is that if we start with captured CO2 with the dianion, and we start to oxidize it to the oxidized form, which should release CO2, we see that CO2 is released, which is shown here by the headspace. And then in black is the charge. And then if we then cycle backwards again and we re-reduce it, we can see the CO2 is recaptured. So this happens, like I said, our cell is not ideal at this point. It happens over the course of many hours. And the reason why this doesn't go quite back to zero is because there's slow gas diffusion in that cell. But the important point, I think, about this is that we get O2 stability that are conferred by these hydrogen bond donors, which are simple alcohols. Based on our KCO2 and E1/2, the energy efficiency is about twice as good as alkylamine thermal flue gas capture, and about twice as good as at the time best reported ECC, which is a few months ago, but lots of things have been reported since then. So I have to check that out. And then, of course, it's composed of these 2 commercially available compounds. So, you know, in terms of catalysis, you know, I like to do electrocatalysis. It's sort of been a big component of my group. You know, it's very popular now to talk about using electrocatalysts to replace traditional thermal catalysts for a lot of the things that we often do industrially. I believe that the things that we do thermally now are very efficient and streamlined in a way that we may not be able to replace most processes, but I think that there are real opportunities in thinking about doing some things electrochemically. You know, in some cases, you can access non-thermal products that you wouldn't be able to do otherwise at high temperatures. They're better for distributed manufacturing or maybe smaller operations because there's lower infrastructure requirement. In principle, the sources of feedstocks are more widely available, and it's more modular. So I don't think it will replace, maybe not even a lot of thermal catalysis, but I think there are definitely places where electrocatalysts can make a contribution in the future of catalysis. Wanted to thank my coworkers for working on this. Up here are the people who worked on CO2 reduction, and here are the people that have worked on the capture and concentration project. We collaborate on that project. I didn't get to talk about some of the collaborative work today, but we work with the theorist Anastasia Alexandrova at UCLA and Vic Bruchette, who's our engineering colleague, who will be helping us with the cycling in the future. I'm happy to answer any questions.
Thank you very much, Jenny. That was really superb. Any questions for Jenny? We're going to need a... Okay, sorry, you go first. Yeah, sorry, you go first. No, you go first.
Hi, thank you. That was a really nice talk. Obviously, one of the issues with amine sorbents is NOx, SOx impurities. How much of an effect do you envisage these will have on your materials?
That's a good question. I think chemically we don't expect it to, but we haven't tested it yet. And it's actually on our list of things to do, is to basically make, you can buy simulated flue gas, or basically, in our lab, make things that have EPA limits on flue gas and see whether they're affected. But that's an excellent question. Yeah, chemically we don't see how they would react, but we'd have to just do the experiment.
Jenny, I had a question about your maybe lack of understanding on my part. What happened? The alcohol that you add to your system, the last system you were talking about, is it consumed in the electrocatalysis, or is it?
No, actually, it's just an additive that it's sort of like, you could call it maybe solvent engineering a little bit. We're basically using it to help get the properties that we want from our capture agent, but it is not consumed. I assume you're talking about the capture.
Jenny, this is absolutely fascinating. With your capture agents, the quinones, are they the optimum, or have you got ideas for how this can be improved? Because you said they've been around for some time, and maybe there are other ones, because I suspect you're limited at the moment on flue gas rather than going to direct air capture with the approach you've got with that.
Yeah, so we would love to get, so one thing that's interesting is that we actually, for efficiency purposes, and our engineering colleagues have built models for us to talk to us about what the ideal properties are, but we actually don't want to be too far into this region. We actually want to be close to the line to do the most efficient capture, because as we go this way, we basically spend too much energy in the capture, which we then have to pay back when we cycle again. Yeah, so we are working both on improving and getting more capture agents that work in flue gas, but really our target has long been atmospheric. And you're right, the Quinone work, which was mostly done about 20 or 30 years ago, they sort of hit the limit there, but we now have better tools. So Anastasia, our computational collaborator, has done machine learning to sample many Quinone derivatives in order to see whether or not, which ones that are most likely to deviate from these properties and go sort of this upper right corner as well. And we also think that there are various things with electrolyte engineering as well, or solvent engineering, that we can do to basically help us get into this region. I mean, the air stability is really the problem. There are plenty of things that will work on atmospheric concentrations, but they're just not stable to air.
Yeah, that's a big problem.
There, as I said in my group, there's no CO2 capture application that doesn't have oxygen present, so we have to figure this out.
Thanks.
Okay, I think we should move on. Thank you once again, Jenny, for your lecture.